Good morning, everyone. Thank you for joining my presentation. My topic is a study of tower and valley steel concrete connections of a prestressed concrete spar supporting a 10 megawatt floating offshore wind turbine at Wichuda, a Ph.D. candidate from Yokohama National University, Japan. Presenter and author. Co-authors are Mr. Han Sang, Professor Rodolfo, Professor Fujiyama, and Professor Maegawa. This presentation includes introduction and background, research objective, research methodology, results and discussion, and the final is conclusion. Here is the background of this research. In 2019, Japan implemented a new law to promote offshore wind farms to be operated by local and foreign companies along Japanese coastal water, around 30,000 kilometers. However, greater than 90% of Japan's annual wind energy generation potential locates in the deep ocean that will require floating platform technology. Among other floating platform concepts, a gravity-based spar platform exhibits small heave motion because of the deep draft. This is advantageous for power takeoff cable, umbilical, and mooring system. The deep draft means that spar platform cannot be used in shallow water. However, the simple cylindrical shape of the spar-based concept has been shown to achieve cost reductions. In Japan 2012, a half-scale model of a hybrid spar mounted with a 100 kilowatt wind turbine was installed at Goto, Iceland, Nagasaki Prefecture. After that, in April 2016, a full-size 2 megawatt wind turbine was installed at the same location after the previous one was removed. Horsepower hybrid structure in which the upper part made from steel and the lower part made from prestressed concrete. In 2014, the Fukushima Forward Project Phase 2 constructs 7 megawatt advanced spar made from steel. When we talk about steel platform, the decreasing of fatigue life because of corrosion in the connection joint is one of a crucial concern. As a result, concrete materials have been increasingly used to develop offshore substructure because of their advantageous properties. Most research has studied the use of reinforced or prestressed concrete. However, the use of precast segment prestressed concrete has not yet been widely investigated. My research therefore aims to develop a concrete spar supporting a 10 megawatt floating offshore wind turbine using precast concrete segments prestressed by a post-tensioning system. Here are the advantages of this approach. The concrete segment can be cast at any press before being transported to the fabrication site. The unbound post-tensioning system is chosen because this method eliminates grouting operation, certifying economic aspect of this study. The pre-compressions induced by precessing force considerably increase the external force required to crack the concrete. This can prevent steel connection joints and reinforcing bars from corrosion. In addition, unlike steel fabrication, the production of precast concrete segments does not require highly skilled labor. Workers in any local communities can do this job. In this research, the analysis were performed into two parts. First is parametric stability and motion analysis to define the geometry of the spar. Structural response under wave action will be evaluated by WAMIT. The coupled dynamic analysis of the system will be performed by OPEC-FAST. Second is finite element analysis to investigate the nonlinear behavior of the concrete structure, which will be performed by finite element code COM3. The IEA 10 megawatt was used as the reference wind turbine wave condition from location around Japanese Sea, performed in three conditions: operational, storm, and centenary, and they were described by ISSC wave spectrum. Three wind conditions performed with irregular waves, maximum moderation, and cut-off wind speed of the wind turbine, and typhoon conditions. A parametric study on hydrodynamic motion analysis was first performed to define the geometry and verify the behavior under wave action of the proposed spar. In the previous study, the spar was defined using 11 parameters in the parametric analysis. Finally, we got the structural geometry that satisfied both hydrostatic and hydrodynamic equilibrium and can avoid structural resonance induced by wave excitation. This can be confirmed by spectral analysis of rigid body motion that show low significance response motions compared to the input wave energy, and this is how we can define the shape of the floating platform. From now, we can start structural concrete design. This is the full scale of concrete finite element model. It is composed of around 35,400 elements and 44,000 nodes. As this conceptual design was developed based on the economic aspect, therefore all concrete parts are regular concrete with the compressive strength 41 megapascal. The static load applied to finite element model were obtained from the dominant case of open force analysis. The results show that the highest force occurred under the rate wind speed in storm conditions. These forces were applied at the bottom of steel tower and at the valid connections as 20 times the monotonic static load. This is the 5 study case of finite element analysis. Study case 1 is a normal reinforced concrete with 0.1 reinforcement ratio. Case 2, a normal concrete with 1% reinforcement ratio. Case 3, apply design tower connection to case 1. Case 4, apply design mooring connection to case 3. And case 5, apply design precessing force to case 4. Here is study case 1, a normal reinforced concrete with 0.1 reinforcement ratio. Localized stress and strain value without applying any connection system and precessing force are shown in figure 4. For a normal concrete, if the tensile strain in concrete is greater than ultimate tensile strength or 200 microstrain, microcracks start to generate. Therefore, the red area in figure A is the critical area that must be strengthened to control crack development. Figure B presents the principal tensile stress, although the red zone was higher than the concrete tensile capacity. However, this stress can be transferred by reinforcing bar. Figure C shows that the principal compressive stress of concrete was mostly less than the concrete compressive capacity utilized in this study. Therefore, the normal concrete with compressive strength 41 megapascal is applicable to design the proposed bar. Here is study case 2, a normal RC with 1% reinforcement ratio. The result shows smaller red area compared to case 1 because more steel being implemented. However, the strength and strain concentration still has high potential at the steel concrete connection part. Therefore, it is necessary to design the connection system at the critical location to lower the stress and strain. In study case 3, a preliminary design tower connection was designed. The embedded steel ring with triple lips layers was first utilized. The results show the pattern of strain distribution change after implementing the design steel rings. The strain has now accumulated in high concentration at the steel lips and at the valleys. The tensile strength of the critical elements located at the top lips and at the valid locations was still much greater than the ultimate tensile strength. In study case 4, a preliminary design mooring connection is applied. In the study case, the valid region was investigated. This location is subjected to large tensile force from mooring lines. This force was considered to be received by 2 layers of steel rings with triple connection plates rather than by reinforced concrete, and the results show the strain at the valid is now lower than the limit. This confirms the applicable design mooring connections. The strain at the tower connection were reduced, however, it was still higher than the concrete ultimate tensile strain. Therefore, pre-stress design is necessary to strengthen this critical area. In study case 5, a preliminary design precessing force is applied. In this case, surrounding area of the rib plate is the area to arrange pre-stressed tendons. The preliminary precessing force was applied to 7 tendons. Utilizing multi-strand anchoring system, as shown in figure A, the strain distribution after applying precessing force shown in Figure C, where the red highlighted area is now left only at the top limits. Case 5 stress-strain relationship in C exists, and the maximum principal stress-strain relationship of the critical member are plotted together with Case 3 and Case 4. The analysis results show that the concrete strain is greatly reduced, particularly in C axis, with the concrete walls pre-compressed by pre-stressed tendon. The strain is now lower than the ultimate tensile strain. The principal tensile strain is also reduced nearly to the limit, which is acceptable. The inclination of tower in vertical and horizontal directions subjected to the bending moment of the wind turbine under operations are presented at the MV diagram. In case 1, the tower deformation has increased linearly in proportion to the applied bending moment. Similarly, case 2 shows smaller deformation because a higher reinforcement was implemented. For case 3, 4, 5, the linear graph has changed to steep slope due to applying design connection system and precessing force. It shows much smaller tower deformations in both directions compared with case 1 and case 2. This could imply that the connection system and precess design successfully prevents the tower from large deformations. This is the example of structural displacements of case 1 and case 3 before and after implementing a tower connection system. We can see that the connection system successfully prevents the steel tower from bucking failure and pulling out of the concrete spar floater due to large bending moment during wind turbine operations. Based on the results, the following conclusions were obtained. The normal concrete with a compressive strength of 41 MPa can be used to design a spar concrete. A concrete strain that is over the ultimate tensile strain will initiate crack. This area is the critical area for designing precessing force. The preliminary design of tower connection could change the pattern of dispersal strain distributions by accumulating at the steel lips, which is useful for structural design. The preliminary design for the valid connection successfully resists the last tensile force transfer from milling lines. It could also prevent this force from transferring to the critical zone located around the tower base area. The preliminary connection system and pre-stress design have successfully prevented steel tower from bucking failure and pulling out of the concrete due to large bending moment under the operation of the wind turbine, as well as the crack generation and propagation in concrete parts of the proposed spar. And this is my future task: apply dynamic force of tower base and mooring tension to the finite element model, logic life analysis and experiments. And the final is propose a spar concrete and steel concrete connection system supporting a 10 MW floating offshore wind turbine. This is all of my presentation today. Thank you very much for your attention.